All right, hello. I'm going to go through pre-calculus section 7.5 right here on parametric equations. Now you may have seen parametric equations before, like if you take physics. So you probably haven't seen them before in Algebra 2 or anything else, but this is what they look like. A parametric equation is usually in physics because you are trying to separate your horizontal and your vertical motion. And so if you're talking about projectiles, a lot of times you use this setup here because you are moving at a certain angle and with a certain speed. So you can see V right there. V is your initial velocity, that right there, and t is your time, h is your initial height, and you have the angle that you're moving at. So and a picture of somebody throwing something there, and so this is what your equations kind of look like right here. You have x and y, and they have the variable t in them, and so you see x and y are separate. And so we're going to talk about how to graph those and also how to turn them into regular equations that you're used to with x and y. And also a lot of times you have limitations on t, like this one says from 0 to 4. So a lot of times, like I said, t is standing for time. And so a lot of times you're starting with t equals 0 because you can't do negative time. But also many of the graphs, you see they have these little arrows on them kind of pointing you in the direction. So basically when you begin, that's the direction it takes until when you end. So let's see how this works. So just have a couple statements here if you want to jot those down. You normally write equations and functions in terms of x and y. Parametric equations rely on the variable t, and usually that's meant to stand for time. So with parametric equations, movement is broken up into horizontal motion and vertical motion. And as t changes, the function kind of moves. And so, a lot of our problems, we can say, x equals, like you saw on the last page, like the first one we're going to do is x equals 2t, and y equals t squared plus 5. But somebody could also write this, x of t equals 2t, and y of t equals t squared plus 5. It just depends whether they're writing it in function notation or just regular basic notation. All right, so let's get started with our first equation here. So our first example is going to be just what I wrote in the last page. I have x equals 2t and y equals t squared plus 5. All right, and I'm going to tell you that t is going to stay between, t is going to be between -3 and 2. All right, and so when you do this, a lot of times it's advantageous to, you can make a table or you can turn it back into like a regular rectangular equation. If you make a table, what you want to do is you want to basically list your t values, and then you have your x and your y depending on that. So you need like 3 things. So like usually I do -3, -2, -1, 0, 1, and 2. And then you just basically figure out the answers for those things. So like if t is -3, then what I'm going to do is plug -3 into here, and -2, and so on. So I'll just do one at a time. So let's see, -3. 2 times -3 is -6. 2 times -2 is -4. I got -2, 0, 2, and 4. And then plugging it into here next, I would get -3 squared, so 9 plus 5 is 14. Then I will get 9, then I'll get 6, then I'll get 5. 1 plus 5 is 6, and then 9 again. All right, so if we make ourselves a little graph, so that's why I chose some graph paper here. So I'll just do a quick graph. I'm going to show you on Desmos how we can get that done as well. So this is going to be with x and y. All right, so you just graph the points. So you're saying to yourself, okay, -6 and 14. So -1, 2, 3, 4, 5, 6. 6, 7, 8, 9, 10. I don't have enough space here, so I'm just going to kind of fake it here. We're going to see on the picture. So -6, 14, I'm just going to like go 1, 2, 3, 4, 5, 6, and I'm going to just go like about up here, -4, 9. So that would be maybe about here, and -2, 6. I don't recommend this. So maybe about there, 0, 5. Then 2 back up to 6, and then 4 back up to 9. All right, so we get this picture that starts here and kind of wraps around to here. And it stops right there. So it starts and it stops. It has a hard start and hard stop. And so when you do that, you can denote the fact that these points came in this order. And so that's your basically motion. All right, so if you're on Desmos, if you go into Desmos and type in parametric graphing, then, oh darn it, it went away. Oh, no. Hang on. All right, well, let me go back to that again because I just lost what I wanted. All right, so if I go here and I go ahead and type in, want 2t, so 2, and then you have to go to your t there, and then I have t squared plus 5. So you gotta go grab t squared plus 5. And so Desmos knows that it's a parametric equation. And so I want this to go from -3 to 2. And there it was. So see, this was the picture that we had before. It was a parabola. And let's go look and see how we could change it back to a parabola equation, because you can see that it is. All right, so what you would do then is you would go and you solve one of your equations. You take one of these equations right here, one of these or this, and solve it for t and plug it into the other one. So it's easy to solve the x one for t. So I'm going to do that. So x equals 2t means I have t equals x over 2. And then I'm going to plug that in for t right here. So I get y equals, I have x over 2 squared plus 5. So I get the equation y equals x squared over 4 plus 5, which pretty much matches what we saw on Desmos. It was crossing at 5 right here. It was a parabola facing up. Anyway, so you can kind of get the endpoints by doing the beginning and the end right here and where to start and stop. But that's basically it. All right, so we're just going to do a couple more. Let's see, the next one. So I get x equals 3t and y equals t plus 2. And I'm going to say where t is an element of the set of numbers -2 to 3. So I'm going to limit myself from -2 to 3, and that'll be that. And so actually, why don't I change this to make this a little bit easier? I'm going to say from 0 to 3. Okay. All right. So if I want to make an equation out of this, like a rectangular equation, let me solve this guy right here. I get t equals x over 3. And then plug that into there. So I get y equals x over 3 plus 2. So that's just an equation of a line. So when I graph this, I should get a line. So you can, if you want, just take that rectangular equation and graph it. I mean, it's the same thing, 1/3 x plus 2. But I got to start at 2 and go up 1 over 3. But when you do it and you graph that line, you don't know where to start and where to stop. All right. Okay, so what you have to kind of do is plug in the initial and the terminal point. Like when t equals 0, you get the coordinate 3 times 0 is 0, and 0 plus 2 is 5. So that means, I'm sorry, 0 plus 2 is 2. Duh. Sorry, confused myself. All right, so that means that this graph starts right here. And then when I go ahead and, plug in 3, obviously I get 9 and 5. So that means that this guy over here, right here, was the end. So I start here and stop there. So I want to erase everything else around it because this graph is not supposed to keep going. It's only supposed to last when t is from t equals 0 to t equals 3. So like, let's say 0 seconds to 3 seconds. And then I also want to denote that it's going this direction when it moves. And there we go. And that's basically it. All right, so we're just going to do a couple more that get a little more complicated. So here's our next one. X equals 1 over radical t, and y equals t plus 1 over t. Now this one I'm not going to restrict you at all, but because of the nature of these equations here, t is restricted. For instance, right down here, t can't be 0 because 0 on the bottom of a fraction is not going to work. And in this one, t can't be 0, but also that's inside of a radical, so you can't use a negative t value. So if somebody asks you for the domain of your parametric equation, you have to look at your places where t is and ask yourself, what is it allowed to be? So my domain here is going to be that t has to be greater than 0, and it can't equal 0, so I'm just going to stick with greater than 0. All right, so 0 and on. So my domain is basically from 0 to infinity. So that means that this thing just keeps going forever, and let's see how it looks. So if I want to change it to a rectangular equation, let's go ahead and do that first. So if I take this one, x equals 1 over radical t, I'm going to like kind of cross multiply and get x radical t equals 1, and then get radical t equals 1 over x, square both sides, and get t equals 1 over x squared. Okay, so now I'm going to plug that into my next problem. I got y equals 1 over x squared plus 1 over 1 over x squared. So I'm going to flip this up and multiply it. So I have 1 over x squared plus 1 multiplied by x squared over 1. So that is my equation for y. So I'm going to get, when I distribute right here, I'm going to get 1 plus x squared. So a parabola. So when I graph this thing, it's going to be a parabola. And so a lot of times it's easier to graph it when it's in its rectangular form. So I get 1 plus x squared, and so, or x squared plus 1, and so that would be this parabola. That would be starting up 1, and parabolas go out 1 and up 1, out 2 and up 4, and so on. All right, so I have this whole parabola. But I need to check where to start and where to stop, and like which direction does it go. So remember that t was supposed to be greater than 0. So if I do plug in like something like right past 0, so like, I don't know, like 0.1, or even I could even go as far as 1. So if I plug 1 into here, I get 1. If I plug 1 into here and here, I get 2 over 1, which is 2. So it's look like it's like this place right here, but that's me plugging in 1. So pretty much what happens here is that this thing existed before that a little bit, because I was starting with t equals 1. So it went, I could have started at like 0.1 or 0.01, because anything greater than 0. So I'm going to kind of surmise here that basically this graph lasted from here on, but it also lasted like right up until there, not including that point at 0, 1. All right, so I'm going to erase everything else off this picture, and then I'll get my graph. So I'm going to erase that even. And let's see, I'll draw an open circle there, and it's going up like this on forever. But again, you can graph these things on Desmos if you like to. All right, let's see, I think we got enough there. Let's do one last example here. Whoopsie, I don't have any more pages. All right, so for my last example here, there are going to be some that are a little bit different. Let's say we have x equals 2 cosine theta, and y equals 5 sine theta. So you saw this on your on Desmos there when I first entered it there, but we'll go back to that in a minute. All right, so we're going to have to find a way to relate x and y with sines and cosines. And I want you to remember this little trick before. Do you remember that sine squared theta plus cosine squared theta equals 1, right? All right, so we're going to use that to kind of help us out, because I don't want to have to graph this with all different values of theta. This is kind of like what you did with polar equations. I mean, you remember this a little bit, right? And so we don't want to have to go to that. So let's solve this for cosine and sine and plug it into our formula. So if I solve this one for cosine, I will get x over 2. Solve this one for sine, I will get y over 5. So I'm going to plug that in. Sine is y over 5, so I'm going to have y over 5 squared, plugging it in here, plus x over 2 squared equals 1. All right, so I get y squared over 25 plus x squared over 4 equals 1, and that should look familiar to you from earlier in this chapter. That's our good old ellipse. So it is an ellipse. It's right at the center, and it is going out 2 in the x direction, and it's going 5 in the y direction. All right, so we have our nice little pretty ellipse right there. All right, and if you want to see how to do this on Desmos, oh, and one more thing. If we want to see the direction, so if I basically start with like theta equals 0. Theta equals 0. When theta equals 0, I will get 2. Cosine of 0 is 1, so I'll get 2. And y will be 5 times the sine of 0, which is 0, so 0. So my first initial point is right here. Let's say we let theta equals pi over 2. So cosine of pi over 2 is 0, so 2 times 0 is 0. And sine of pi over 2 is 1, so 5 times 1 is 5. So that goes up to this point here. So I can tell that this is going around this way. All right, so as t grows higher than 0, then it just keeps going around and around and around. All right, so if you wanted to graph that on Desmos, we can very well do that. And so let me go back to the beginning here because it had our theta in there. Or it had t. Actually, so it'd be better to use t here. And so we have our 2. So you got 2, and if you want cosine, press the functions button. We got cosine, and it's better to go ahead and use t instead of theta. It's a little bit easier, I think. All right, I think I also tried it with theta, and then you lost your little like inequality down below, and so it was kind of annoying. Sine, and then go back and grab my t. All right, and I want 0 between 0 and we'll say 2 pi. So, 2, and then if you want to actually get the pi symbol, you can just type in pi and it knows. All right, and I'll delete this point up here. So there you go. So there's our ellipse, just like we thought it would be. And that is it. And we'll see you next time. Bye-bye.